Right. Welcome everyone to this Monash Cybersecurity Seminar. Today we are happy to welcome Benjamin Diamond, who is a staff applied cryptographer at Coinbase. Benjamin earned his PhD in mathematics in 2017 from Johns Hopkins University, where he studied algebraic geometry. Since then, he has worked as a cryptographer in industry. He spent 3 years at JP Morgan before moving to Coinbase. His interests are in algebraic, combinatorial, and post-quantum cryptography. And today he will talk to us about many-out-of-many proofs and applications to anonymous Zether. Thank you very much, Benjamin. The scene is yours.
Okay. Does that work?
Yep, all good. Thank you.
Okay, cool. Well, so first of all, thanks, Mohammed, for having me here. It's an honor, so I'm excited to present, and let's get started. So I was telling Mohammed I just talked today actually at S&P, so it's been a long day. Also, this is a kind of a longer version of the talk, and with sort of new material, which I haven't really gone through. So part of it might be less practice, but in any case, let's start. So it's well known that regular cryptocurrencies lack privacy, for example, Bitcoin or standard Ethereum. And, I found it's a trend to sort of go through news clippings in the beginning of the talk. So here they are about why, what happens when you use cryptocurrencies which don't have privacy, what the consequences are, right? So this is a real life issue. There are well-known efforts to improve privacy. For example, Monero and Zcash. And these are standalone cryptocurrencies which also include private payment. 1 second, let me turn off my AC. And also do things like handle mining and stuff like that. So now what I'm going to argue in this talk is that these currencies and the sort of other efforts in private payment have a kind of a kind of flaw which actually hinders their use, right? And here's the thing: they've mainly focused on the sizes of transactions, right? So things ZK snarks are succinct, right, and have brought transaction sizes to about a couple kilobytes and reasonably sized blocks. And while this has been successful, I claim that there's a further factor which hinders their use, namely their feasibility with mobile devices, right? And in particular, wallets or really any wallet, right? And the reason is that there's a huge bandwidth burden on these wallets and also a CPU burden. So why is that? Well, because of how they work, it turns out that to even know your own wallet state or your account state or how much funds you own, you have to scan through every transaction which appears on the blockchain, all is sort of constantly, right? And each transaction that appears, you have to cryptographically process to even determine if it's to you or not, right? So in practice, this causes your phone to be sort of synchronized all the time and constantly sort of downloading blocks and things like that. Here is so I've discreetly blocked out the sort of names here, but I claim that this is a real issue in real life. Here are reviews in the Google Play Store for certain apps, wallet apps for Zcash on the left and Monero on the right. And you can see that, it's connecting forever and things like that. So we want to fix this. And I claim that there is an existing approach called anonymous Zether that actually was proposed initially in a paper by Benedict Boons and Shashank Agrawal, Monash and Dan Bonnet, which I claim solves this bandwidth issue and also the CPU issue. And what this means is that your mobile device, your wallet, can basically be off or just offline for any amount of time. And when you go back online, if you want to just know, say, your account balance, you can do this essentially instantly just by downloading some really modest amount of state, regardless of how long you are offline for. Similarly, to send funds, you need to just get some small amount of state. to know enough about the blockchain state to send funds. So this contrasts completely with the kind of existing approaches to private payment. So just real quick to summarize, how does anonymous Ether work and how does it achieve this property? Well, so first things first is it runs on a completely different model from other private payment systems, right? All prior systems are essentially UTXO based in the sense that, roughly they're kind of like Bitcoin, except they add kind of extra privacy, right? So they will do things like conceal how much value is contained in certain in the UTXOs, or also conceal which one you are consuming when you consume one, right? And Zcash and Monero obviously do this in different ways, but roughly speaking, that's what they end up doing. Anonymous Ether is account-based in the same way that Ethereum is, right? And moreover is actually a smart contract, which is kind of pluggable into Ethereum. So that's a kind of separate fact, which actually is not really essential, right? So anonymous Ether could be a standalone cryptocurrency if you wanted, but this was a decision made by Boons and the other authors to target a contract within Ethereum, and I do that as well, right? The benefit being that you can privately pay any Ethereum-based asset, which is really nice, right? So yeah, so not only is it Ethereum-based, so essentially you have a pre-existing ERC-20 and you deploy a linked anonymous Ether contract with prescribed ways to move funds in and out. And the way that private payment actually happens is happens inside the anonymous Ether contract. The storage stores a massive table, right? So again, this is account-based, that's key, right? Where each row of this table is a public key, and the value is an encrypted account balance under that key, right? So, unlike Ethereum where I have just 20 sitting next to my public key, in this case, you have an encryption of 20 under my public key. And under your row, you have an encryption of your balance under your key, right? And the way that you send funds is, if I'm the sender, I pick some subset of this global table, or a ring, you could say, right? Which contains myself, the sender, and the recipient, and then some others who you can think of as decoys. And you encrypt under the respective keys the amounts that you want to change the balances by, right? So I'll encrypt -10 for myself, +10 for the recipient, and 0 for the decoys. And then I'll attach it as zero knowledge proof that shows basically that this takes the right form. We'll talk about this more in a bit. But the idea is that provided the proof passes, the smart contract can apply these homomorphically using the homomorphic property of the encryption scheme. And in the process, we end up sort of making the transfer we want, right? So in particular, it actually will overwrite the prior ciphertext with new ones. And there are a bunch of benefits of doing this, right? So first of all, the space is constant in time per user. So this is not a property that Zcash or Monero have. But moreover, it has the kind of offline quiescence property, right? In the sense that I can sit back and let this happen arbitrarily many times. And when I come back, I just query my own row in the table and download one ciphertext. And at that point, I already know my account balance. Any questions so far? Maybe I can pause.
I'll ask you a quick question. So you mentioned that the ciphertext, isn't this bigger than 128 bits?
Bytes, right? So it's an Elgamal, really.
It was bytes. Okay, sorry. Okay.
Yeah. Maybe I misspoke, sorry.
Okay.
It's really 2 Elgamal ciphertexts, 2 for kind of technical reasons, right? But each one should be something like, 128 bytes.
Okay, yeah.
Okay, anything else? Okay, so this is good if we can make it work, right? The question is, how do we do this zero knowledge proof? And this turns out to be the hard part. Okay, so let's talk about what the zero knowledge proof should show. Intuitively speaking, we want to show that it takes this form on the right. And so in a bit more detail, each element of this list should be a well-formed ciphertext under the right public key. There should be two ciphertexts among this list that encrypt opposite amounts. And whichever of those is negative needs to be authenticated in some sense, right? So the spender should be able to show that they have the privileges to spend from that account. There should be no overdrafts. So whoever's spending funds should not wind up with a negative account balance. And crucially, the rest of the ciphertext should encrypt zero, right? Otherwise, I can sort of alter arbitrary account balances in the course of my transaction. Okay, so let's just like really briefly think about why this is hard to do, right? So each of these things alone is sort of not hard if the indices are visible, right? So it's easy for me to say, hey, verifier, take these two known indices, and I claim that they're Elgamal encryptions of opposite amounts. Actually, this is what basic Zether does, right? So in the original Zether paper, they have a version which is not anonymous, and basically that's what it is. And it's easy to authenticate a known sender's public key. You just use basically a Schnorr signature. And to show that a ciphertext is zero is obviously not hard, right? But this becomes way harder when we want to conceal the indices that the sender and receiver live at, right? Because we can't tell the verifier which two they should check to be opposites and which n-2 they should check to be zero. So you're sort of doing different checks depending on what index, and you also need to keep those indices secret. Is that roughly clear? Okay, well, anyway, so basically what I will present is a zero knowledge proof that does this, which also has good asymptotic and concrete performance, right? And the thing to remember is that in anonymous Ether, you pay for privacy, in the sense that you need to choose your anonymity set size, and the bigger that gets, the better privacy you get, but then performance will degrade in some way. And the question is, what is the nature of that relationship? So in the protocol that I'll present, the proof size grows only logarithmically in the size of the anonymity set, which is good. The prover runtime is quasi-linear, so n log n. The verifiers also is. And the transaction size, of course, is linear because you have to attach this array of ciphertexts, but still has pretty reasonable size in practice. And then finally, it only uses standard assumptions and has no trusted setup. Okay, so before I actually tell you how this gets done, or even what a many out of many proof is kind of rigorously, I claim that this gives you some pretty nice applications, right? So for example, I can show you a vector of commitments. I can claim that I can open these to a standard basis vector, but not tell you which standard basis vector. So one is 1 and the rest are 0, but I won't tell you which is 1. I can tell you that after the messages, after shifting these by some offset, they wind up, the resulting vector lives in a prescribed hyperplane, but I won't tell you what the offset is. I can show you that either all of the even indexed commitments I can open to 0, or all the odd indexed ones, but not tell you which of those two. These are, basically richer statements than you can prove with regular one out of many proofs. Okay, so let's talk about how you do this. Obviously, the starting point is the paper of Jens Groth and Markov Kohlweiss, one out of many proofs. And what this does is take a public list of commitments, which the prover and verifier both have. The prover knows one among these and a way to open that one to 0. Now, what you prove is basically knowledge of the secret opening and the secret index, right? So which one you're actually opening. And in the eye of the verifier, the index should stay secret, right? So what I want to do here is is to, instead of thinking about a single secret element, to think about a secret subset, actually a secret ordered subset where both the order and the subset and the order are secret, right? And just really starting with an example here, right? So this looks like an anonymous Zether transaction on the right. And what we end up showing is that if you go through this list of ciphertexts in some order, in a secret order, then you wind up with a second list which satisfies certain linear equations, right? So in this case, you know, for example, the top two add to 0 and the rest are 0, right? So this should look familiar. This is basically what we want to prove in anonymous Zether, right? And the key privacy property is that in the eye of the verifier, it should be secret what that reordering actually was, which caused these linear equations to get satisfied, right? In particular, the indices that the sender and receiver live at should stay secret. Okay, so how do we achieve this? So to understand how this actually works, we have to first understand how regular one out of many proofs works. Okay, so if you look back at that paper, what you find is that the first step is basically the prover comes up with and in some sense commits to a list of polynomials. And so the property of these polynomials that matters has to do with their degrees. So at the secret index, the polynomial should be of high degree. It should be of degree m, which is log of the length of the list, and it should be monic. And the rest of the polynomials will be of lower degree, right? And after getting a challenge, the prover can respond with the evaluations of these polynomials at that challenge. So the verifier gets this list of lowercase p's, right? And the verifier is basically convinced that these take the right form, right? Namely that they are actually evaluations of polynomials which have the right structure. And moreover, the prover can convey this information to the verifier using only log n communication, which is an interesting and non-obvious fact, which is explained in the original paper. And the idea is that if the verifier takes a kind of dot product between the initial list of commitments and this new vector, then by construction of the lowercase p's, what the verifier gets is none other than the secret index, which the prover chose, raised to a high power of x, and then plus lower order terms that involve only lower powers of x. And the prover can anticipate what these are and sort of send the appropriate correction terms before seeing X. And you can show that this winds up being sound, right? And moreover, obviously, the verifier learns nothing about which index it's sitting on because these lowercase p look random to the verifier. Okay, any questions? Okay, yeah, it's a bit tough because I can't see any of you. So, oh wait, yeah. Anyway,
there is no question in the chat.
I see. Okay,
we can proceed.
Cool. So what about many out of many proofs? So I claim that there's a really powerful technique that's basically being left on the table. What is that? Well, let's rewind to this point in time. Okay, so the verifier has a vector of scalars, which takes this very special form. And even though the verifier knows nothing about which index has the high degree polynomial in it, the verifier can still permute this vector and know wherever the index started, the verifier can have some idea of where it is now, right? In other words, as you permute this thing successively, you know what kind of paths can be traced through this vector throughout the course of the permutations, right? And you can sort of do a dot product each time, roughly speaking, right? So, you know, back to this example, we start with the regular dot product, but then you permute this vector. And, you know, in this example, it's a kind of two-step circular shift permutation. And the verifier still knows nothing more than it did about the secret index, but it can do another dot product and get some additional vector and sort of keep permuting this and keep doing this until you cycle through the whole vector. And what you then get is a secret ordered subset of the original list, which takes some special form, right? but both the order and the contents are secret, right? And then obviously lower order terms, but it turns out that you can still kind of cancel these out. It's not as simple now, but roughly speaking, you can up to details. And what you then get is, you get this vector and you can show that this satisfies any linear map you want. So either they're all 0 or they live in some hyperplane or something like that.
Can I ask a question here?
Sure.
So here, when you get these like C5, C7, C1, C3, do you prove that their sum is going to be a commitment to 0, or can you prove some other things?
Well, okay, so it is up to the prover and verifier to decide what linear map they want the C's to satisfy, right?
Okay, that linear map applies to the final C1, C,
applies to the
C5,
yes,
C.
exactly.
Okay,
it applies to this vector of 4 elements, right?
Okay, yeah.
So we can have a linear map from F4 to something lower dimensional, right? And we can show that the messages are in the kernel of that map.
Yep. Okay.
So let me just give a bit more technical view. So again, so our map is from, so we have a permutation of, let's say, order O. So if O was 4 in the last case. And then we have any linear map. So S, the output dimension could be 1 or it could be 4, right? So for example, we could just take this to be the identity map, in which case you're arguing that they're all 0, right? Or you could take it to be the sum, as you said, or anything else. And what you then do is to say that there's some starting element, say L, and for any such L, you can then consider the so-called orbit, right? Which means the iterates of L under this known permutation, right? So L and then kappa of L and then kappa squared of L and so on and so forth up till you go through the whole orbit. So if you're familiar with the idea of a group action in algebra, this is where the idea of an orbit comes from, right? And what you're showing is that for some L, which I know, the prover, if you then go ahead and take the ordered orbit of L, then that will map out some sequence of commitments. And what I'm showing is that if you apply this linear map to that group of O commitments, then you wind up with 0. Okay, so just to hammer in this point, I will give you yet another view on how this kind of looks. Okay, so from the view of the verifier, we can start with this list and then permute this list and keep doing this until we run out of permutations, right? And what the prover is showing is kind of some row in this picture, right? So you start with some initial element, L equal 5 in this case. And what you're showing is that if you take the ordered orbit of L, then you get some further list of commitments which map to 0 under this linear map. Okay, so the length of this input vector is the order of the permutation, and so then this matrix is an O by S matrix, and then you want to show that if you take this output vector, which is a vector of S elements, then openings to 0 of that vector. So that's basically what you're showing. Now there's a technical point. Yeah, any questions about that?
This linear map is public, right?
Yes, correct.
Okay.
The linear map is public. What's secret is L, basically. L and then the openings to this final vector on the left, right?
Yeah. So if this map was secret, that would be much harder, I guess, right?
Well, it's not clear what that would mean, right? Because you can always find a linear map which takes these to 0. You could make it the 0 map or something, right? So
yeah, maybe that doesn't make a lot of sense.
Yeah. I mean, so here, let's just go back to let's go back to the example of anonymous ether, right? So in that case, what is the map? Well, this map is of course public, right? Because what it's doing is adding the first two elements and then keeping the rest of the elements, right? So this Greek letter psi or whatever, right, is a n-1 by n matrix, right? Where the top row is two ones, and then the rest is an identity matrix on the remaining n-1 elements, right? Or n-2, sorry.
Yep. Yeah.
So it makes sense that that map should be public, right? What you want to conceal is the secret ordering that that gives you a satisfying list of commitments, right?
Yeah.
Now, as a sort of trivia question, for the audience, can we convince ourselves that this is really a generalization of regular one out of many proofs, right? So in other words, in order to recover the classical case, what should we take Greek letter psi to be, and so on and so forth, and kappa, of course. Okay, any guesses? I can just say, so.
Do you want me to answer?
Oh, if you have a guess, then yeah, go for it.
Yeah, I think there will just be a single one and the rest is 0.
So close. So kappa should be the identity permutation, first of all, right? So in other words, S is one, the order O is 1. So this vector on the right has just one element, right? You don't do any permutations in that case. You just do one dot product and you're done, right? But the order of the identity permutation is just 1. It's already the identity, right? So there is no cycles to go through. And then the linear map should be what? It should be just the identity map on one variable, right? Because to satisfy that map just means to be 0, right? Okay, so just to repeat, so you can recover classical one out of many proofs if you take kappa to be the identity permutation, and then you take psi to be the identity map on one variable. Okay, any questions? Does that make sense, or can I clarify? Sorry.
Yeah, I think that makes sense.
Okay.
But I think if we were to put a single one in the linear map, regardless of what kappa is, what will come up with is just a single CI, right? That is the.
Okay.
And
well,
you will prove that that's that's kind of makes things more complicated. Of course, you are using kappa for no reason, but.
Well, at that point, it's more of a formalism because you can just get rid of it and forget it existed, right? But it's still interesting to, but yeah, you're right that if kappa is the identity, then the linear map, so there are not many really interesting linear maps on one variable. Essentially, either it's of rank 1 or rank 0. So at that point, either you basically have the identity or some non-zero scalar, or you have 0, which is an even less interesting map because then it's trivially satisfied, right? So there's nothing to prove.
Yeah.
Okay. Okay, so I might skip through this part and we can come back to it. But it turns out that there's actually a really difficult aspect of these correction terms. And this is the kind of thing that, when you're coming up with these ideas, you think should be easy and then ends up being actually the hardest part of the entire process. So it turns out that we still have these lower order terms floating around, which we have to get rid of, right? But the problem is that in practice, S can be large. It can be actually omega of n or theta of n, right? So we can't just send a correction term for each of these vectors on the right-hand side, or even on the left-hand side, right? So there is a kind of random linear combination trick which shows up in bullet proofs. Roughly speaking, the idea is that if the verifier chooses a random scalar, then what you get, you map this down to one dimension from whatever dimension, from dimension S down to 1 by applying these powers of V. And then what you send correction terms for is this entire product, right? So that allows you to send only log n correction terms instead of something like S log n, okay? And that's crucial to make the proof size actually be logarithmic, which is what we set out to do at the very beginning. So claim this is still sound. You have to be careful with this because if the prover sees if the prover sees X too early, X is the last challenge, you have problems. So the prover needs to commit to the polynomials, then get V, then send the correction terms, and then get X. So you actually have a 5-round protocol instead of a 3-round protocol. And interestingly, the communication you get is the same as one out of many proofs, literally no bigger, which is pretty cool. Okay, what about computational complexity? Okay, so I claim that if you unwrap all these constructions, then what you wind up with is the vector of lowercase pi on the top row of a matrix. And then the subsequent rows of the matrix come from applying this permutation kappa to this initial vector. Now, if kappa is a shift permutation, then this is a circulant matrix, and you can actually use the number theoretic transform, which is a kind of prime field variant of the Fourier transform, in order to make this multiplication be quasi-linear time. All right, so this turns out to be a discrete time convolution, which you can do quickly using these recursive algorithms for the fast Fourier transform. So this is, if you don't notice this, then you're stuck with order n squared computation, which you don't want. So this is actually pretty important to figure this out. Technically the prover has to do this for each degree, 0 up to m-1. So this is actually log squared n for the prover and log n, this should be n log squared n and n log n. So let me just do that. Okay, so any thoughts or questions about this? In anonymous Ether, you can actually get rid of this extra factor of log n by doing some additional tricks, but that's more of a technical point. Okay, so apologies for the typo. Any thoughts or comments? Okay, so let's look at actually anonymous Ether, because for the past 20 minutes, I've been just talking about many out of many proofs in the abstract. Okay, so with this tool in our hand, how do we get a good protocol for anonymous Ether? So the idea is that you run many out of many proofs twice, once for the sender and once for the receiver, and you kind of interleave the two executions. So let's start with running one out of many proofs twice. So in the view of the verifier, we basically get two rows of a matrix, one of which secretly identifies the sender's index and one of which secretly identifies the receiver's index. And what we're going to do is actually shift both of these to the right by 2 steps. And we're going to keep doing that until we finish the matrix. Okay. And what we want is that this should basically be a permutation matrix, okay? And whether this is a permutation matrix or not actually depends on the parities of L0 and L1, okay? So this is how we want it to look. So these point to some secret indices. So we're now sort of putting on the X-ray glasses of the prover, and this is what the prover sees, is that there are 2 secret indices here, and then these get shifted to the right by 2 steps, and then again and again, and you have kind of wrapping around and stuff like that. And the question is, do these yellow boxes hit each column exactly once and only once, right? Now that's true if the sender and the receiver live at opposite parity indices. and not if not. So if we can find a way of proving that to the verifier, then we should be safe. Okay, in the paper, I give a way to do this, which kind of builds out of techniques that already show up in BCC+. Okay, right, and then so what you then do as the verifier, you kind of take this vector of commitments on the right and left multiplied by this matrix, and what you then get is the reordering you want. Okay, any questions?
Can I set, or can I just set L0 to be equal to L1? Not without using this. I mean, if I want to use this technique, I know it doesn't work, but is there a problem if L0 is equal to L1? Do I want to hide this index from the receiver, for example?
Well, that would mean the sender and receiver are the same person, right?
Ah, so these are different PIs, right? The commitments are different, no?
Yeah. So you the top two rows correspond to completely different executions of the one out of many proof process, right? Actually, turns out you can kind of consolidate them. Actually, you told me this trick. Remember? This is from your paper about lattices.
But I was thinking that, so the sets of commitments where we conceal the sender is the same set as where we conceal the receiver? Or?
Well, okay, but which commitments you have to, can you clarify? Because there were a bunch.
No. Yeah, they are the same set because like both -10 and +10 in your example.
Yes, correct.
Were part of the same set. Okay, yeah, this is different. Okay, yeah.
So yeah, let's go way back. This is what it looks like. This vector on the right is the key vector, right? So in this case, the sender is at index 2 and the receiver is at index, 5, I guess, right?
Yeah, I was basically saying that, how about you take this as one set and this as another set, and now they put both of them at the same index, receiver and the sender.
Okay. So
this reduces the anonymity, of course, at it.
So one design you could do, which maybe this is what you mean, you can clarify if not, right? Is that when you could design anonymous Zether so that the sender pool and the receiver pool were distinct.
Yep.
Right.
Yep.
So I say, here's a list which contains the sender and a list that contains the receiver. Actually, that would work, but it's less good because you actually are losing privacy, right?
Yeah.
It's better if we can conceal, we don't even know, in other words, the graph structure looks different. Actually, let me draw a graph. I mean, you get more lack of information if you have one pool that contains both the sender and the receiver, but we don't know where, right? Yeah.
Basically, the anonymity level is
higher, exactly. So think about if in this case, what would if you put those things back on, maybe you erase them. If you did do that, then how many possible pairs would there be? Well, there would be like 16, right? Or something like that. Ignoring the parity requirement. It's complicated because there's also parity. So let's just look at what the graph looks like, right? Okay, so look at this graph. This is basically the graph of all possible pairs, incorporating the parity requirement, right? In other words, let's draw red for an even index and blue for an odd index. Now, the possible pairs of L0, L1 are basically all possible ways of picking a blue dot and a red dot. So this is the complete bipartite graph on n nodes, right?
Yep.
So having this parity requirement does decrease privacy because we can only have bipartite edges instead of all edges.
Yeah,
right.
Yeah, that's...
But what's good is that the arrows are bidirectional, right? So given any pair, it could either be a sender and the receiver or the receiver and the sender. So that's actually pretty good because, you can think of even if you had a size 2 anonymity set, you're still at least concealing who the sender and the receiver are, which you can't do with basic Zether, right? Yeah, so I think it's fundamentally better when you're putting the receiver and sender in the same pool, right?
Yeah, I agree the same.
Yeah. So the number of edges in the complete bipartite graph is n squared over 4, which is basically a factor of 2 less than the number of edges in the complete graph. Okay, so I have an implementation of this. Actually, this should be a dash, not an underscore. It's also mirrored in consensus's GitHub. And so here are some statistics. Actually, the proving time really should be lower because this is actually written in JavaScript. It's kind of on my to-do list to re-implement this in a better language, like either, like Go or something like that. The verification time also, you should keep in mind that this is in Solidity, right? So this is actually a smart contract that verifies this. And this time reflects basically the local EVM node that will run this as a read-only call if you pass it this directly. Gas use is pretty high. So basically too high to use on the mainnet, you would need some kind of L2. So I think this is the end of my official slides. I can say a few things about future work that I didn't get a chance to put down on slides. So I think an important task, yeah, any questions while we're here? Okay. Now, I think one important question in the future is how do you actually pick the anonymity sets, right? So, what the crypto tells you is that, an attacker has no advantage based on the zero knowledge proof from ascertaining who the sender and receiver are, right? But in real life, if you're making a bunch of sends to various people, you need a practical algorithm to pick who those people should be in such a way that you give yourself some plausible deniability. So both that algorithm needs to be written and also on the attacking side. So let's say you want to de-anonymize somebody, how should you go about that by looking at their anonymity sets? Things like that. How are we on time? How long does this usually run?
We have time and we can take questions. And okay. Yeah, I can start with a question actually, and if anyone else has a question, they can follow up with afterwards.
Okay.
The original Zether, is that also anonymous or no?
Okay, so I
don't really know the original Zether one.
Yeah, so the original Zether is basically the sender and the receiver are distinguished, so they're not anonymous and there are no decoys, but the balances are encrypted, so it's confidential, right? So you still have the same picture with everybody having ciphertexts. It's just that the actual transaction looks different, where you have a distinguished sender argument and a receiver argument, and then you have a zero knowledge proof. But in the appendix of their paper, they basically said that you could do anonymous Zether. It's just that there wasn't really, or there wasn't a zero knowledge proof given, right? Mm-hmm. So what remains to do is to say, so they, that paper had a bunch of amazing stuff. I mean, so first of all, they came up with the whole Zether paradigm, and they also anticipated a lot of difficult issues involving this problem. There's a kind of race condition in Zether because you're overwriting accounts, right? So if I'm an honest user, but somebody overwrites my account right before I submit a proof, then my proof will fail. So they came up with a way to fix this, where you have kind of buffering of accounts during epochs, and then they get flushed between epochs, right? And then they also said that you could do anonymous Zether But yeah, so it's just a matter of coming up with this zero knowledge proof.
Mm-hmm.
And that turns out to be extremely difficult, right? Because
Yeah.
of the issues that I mentioned.
Yeah, so they had confidentiality of the transaction amount, but not the payer and payee privacy.
Yeah, exactly. Yeah.
Okay. Any other questions, anyone?
I can actually, okay, so I can say briefly.
I think there is one question.
Oh, cool.
Yeah, Jiang, go ahead.
Just a very quick one about picking the anonymity set. So what will be the main difference between this one and, let's say, picking the mixing side in the, let's say, Monero-like systems?
Yeah, I mean, so it's a related problem to Monero, right? But it's also a different problem because, in Monero, your elements of the ring are UTXOs, whereas here they're people, right? So if I need to pay my, my landlord or my employee a bunch of times, then it's not. So first of all of those sets will contain both of us, right? And it's not obvious how the rest of the people should be picked. In fact, maybe I should pick the same set every time, right? I can throw in like a big bank or something like that so that these look plausibly like payments to or from a bank or something like that, right? But if I actually pick different decoys every time, that might be less good because somebody can then see that the intersection of these sets is just us two, right?
So the concerns here would be that with Monero-like systems, each time, I think they are enforcing that the output has to be a different one, right? There needs to be a new address. And here we have, because that this is a account model, so that the account will stay the same. And there are certain patterns that will be revealed.
Yes, absolutely.
Right. So is that the only difference, or are there any other considerations that you can think about?
I mean, that's a pretty big difference, right? I mean, at that point, they're just fundamentally different systems. But yeah, you're right. That, yeah.
I guess what I meant is in terms of the security concerns. For example, like the timing analysis or the user behavior analysis in terms of attacking the badly designed way of picking the anonymity set. So there are several concerns. For example, with Monero, for example, if you pick the transactions or the public key address that are older than others, then this is likely to be the decoy one. And in our case, probably we don't have this issue because there are accounts, but there might be other issues related. So I was
yeah, right, exactly. So the famous cases in Monero where you have one which is much newer, and then that tends to be the real one, And as you said, I mean, so here that issue doesn't exist, but you have other issues which are kind of related, right? So for example, I should not ever pick random accounts, right? Because if nobody has ever sent them funds or anything, then there's no way they're the sender. Also something like activity. So if I think about this roughly, right, Monero's main attribute is the age of the UTXO. So if you go to the block explorer, they even show you the ages of the UTXOs, and they should have some kind of even distribution or something like that. So I think like roughly you can think of the relevant, the analogous statistic as the kind of activity rate or something, right? So I want to pick a ring whose accounts are in, the proportion of past transactions they were in is kind of the same as the proportion or some. I want to pick a ring that looks like it's a representative sample from the past couple months worth of data or something like that.
So this is more like clustering the kinds of tightly connected graph of accounts, so that this kind of accounts with better weight in the edge will be considered a close contact, so that they could be possibly chosen as the anonymity set to provide a better guarantee in your case, right? For the
Well, I haven't thought of it like edges. I mean, so for example, like there might be a really heavy edge between, Coinbase and, a bank or something, right? But should I include both of them or just one or what, right? I mean, like maybe. I mean, the way I was thinking about it was like each one has a probability of showing up in any ring, right? In other words, take the past year, Goldman Sachs, say, like showed up in 4% of rings in the past year. So maybe with 4% chance, I will include them in my ring, something like that, right? So that way, when my ring is published, it then looks like a random, just like the same distribution as the other ones which are showing up. Of course, I'm in it, so that makes it a bit weirder because I can't control that, right?
So, but this would mean that we may need a global rule for every user to their anonymity set, because otherwise, if we apply different rules by individual users, then that may also leak information about other users' anonymity set, right?
Yeah, so I agree it should be a global rule, but it should also be a good rule, because it can be, if it's not, then, imagine the rule where it's me, you, and random accounts. That would be bad, right? Even though that's a
interesting problem,
yeah. So yeah, I'm actually, I mean, if anybody wants to think about this and then email me, I would be more than happy to carry on the discussion about that.
Yeah, thank you.
Yeah.
I'll just ask one more quick question. Is there a way to kind of refresh your public key in Zether without transferring the funds to another account?
Well, probably not, right? I mean, you can send yourself funds under some new key, but there has to be a link between any two accounts where a payment happens, right?
Yeah, because there is this kind of like stealth addresses in Monero, so there is nothing similar in Zether.
No, I mean, I think that's basically the price you pay for this refresh, this quiet wallet property, right? Because it's because my key is persistent that I then have this. I mean, in Monero, it's like to even link any two transactions, you need to do a cryptographic. There's actually a cryptographic hardness that prevents that. But the obvious price you pay then is that you have to read every single transaction, right?
No.
So, I mean, I think that if you want something that's going to be used by everybody, then this could be the balance point between, privacy and performance. I mean, you don't want a situation like this, right?
Yeah. Any last question, anyone? Okay. All right. I think in that case, we may conclude the session here. Thank you very much, Benjamin, for your very interesting talk. Thank you everyone for tuning in, and hope to see you all in the next seminar. Bye, everyone.
Thanks everyone for attending.
Thank you. Bye-bye.